Hi, everyone, and welcome to another measurement and instrumentation class. In the previous class, we started with the introduction of measurement tools, and we reached this slide of different categories of measurement and instrumentations. There are three different categories. We have mechanical, electrical, and electronic instruments. And I gave some examples about mechanical and electrical and electronics. The vast majority of the sensors that we are using nowadays are electronic sensors. The reason is they're cheap, reliable, fast, and they also provide digital signals, which is easy to process and also manipulate. And also, if there is any noise, for example, we can easily filter out that noise. Now, our focus mainly in this class would be on electrical and electronic instruments. And mechanical instruments, again, most of them have been obsolete right now. Again, my main focus would be on electrical and electronic measurement tools and instrumentation. Yes, so these are estimates. Thank you for bringing. But you don't need to memorize like any of this. This is just for you to know that electronic sensors are usually much faster than electrical sensors. And one thing that I forgot to mention, and thank you for bringing the time up, sometimes we don't need a fast response. Let me give you an example. If you want to measure the humidity and temperature of this room to set the heat temperature on a thermostat, you don't need to do it 100 times a second, or you don't even need to do it once a second. You may want to do it once every 5 or 10 minutes. So an electrical sensor would work sometimes in some applications. Another example is, for example, if you want to measure, the water level in a water tank, you don't want to do it every second. You can do it every 10 minutes, every 20 minutes. Actually, it's very beneficial to have longer intervals. The reason is if you have a remote sensor, the example that I gave you for sucker rod pumps on oil fields, and if that sensor and that system is running on battery, you don't want it to measure every second or so, because you're going to run out of battery in less than a week, in a few days. And you can't go and change the battery every few days. That's the reason it goes into a hibernation mode. It turns on, it takes the measurements every 10, 20, sometimes every half an hour. So if you want to measure temperature, you can do it every 30 minutes. And that significantly increases the battery life of the system. So sometimes, but if you want to measure, for example, distance using a radar, you have to do it 1,000 times per second, because if you're going 70 miles per hour, 1 second is around, like, I don't know, 50, 100 feet or something like that. So it's a matter of preventing a crash. So those systems need very fast and high response, rapid response sensors. And I'll explain more about them. So instrumentation is the process of acquiring data about one or more physical quantities of interest using electrical sensors and instruments. And this data could be used for diagnostic analysis, design, or controlling a system. Every engineering discipline uses electrical instrumentation to collect and analyze data. The following examples that I'm gonna provide illustrates different types of sensors and instrumentation and different engineering discipline use. So the first one that we have here is called a strain or a strain gauge sensor. I brought some of these sensors. This is an example of a strain gauge sensor. They may be in just one direction, like X axis, or they can find the stress in 2 axis or even 3 axis. Now, how does a strain gauge sensor work, for example, in civil engineering? If you want to design a bridge, you want to design and gather data of the load as well. If the truck is passing or a car is passing, and a strain gauge works by providing the strain data, meaning how much strain is on that bridge. So you can be able to properly design the bridge and also maintain the bridge. So if you want to, I don't know, if you want to, redesign the bridge, add some steel bars or something like that, you can do it with the strain gauge. Now, how does a strain gauge work? I gave you an example of that. A strain gauge usually looks like this. It works on the basis of resistance. And when you pull on both ends of the strain gauge, what happens is, let me draw you. You have to draw that. The principle of a strain gauge works like this. Just give me a second to bring up a pen. So we know for a wire, if we have a wire, we can find the resistance of the wire using this equation. R is equal to rho L over A. Do you remember this equation from principles? What is L? L is the length. What is A? A is the area of the wire. So the thicker the wire is, you have less resistance. If the wire is thinner, you have more resistance in the system. And what is rho? Rho is the resistivity. Okay? Resistivity depends on the material that we built the resistance out of. If you build it out of copper, that resistivity is pretty low. If you build it out of, I don't know, steel, it's going to be higher. So depending on the material that we use, it's going to be different. Obviously, if we want to change the resistance, we don't have any control on the material. The only thing that we can change is the length and the area, the thickness. So the way that a strain gauge works, you see that it has a pattern, a bunch of wires, if you can see inside. And when you pull on them, you are increasing the distance. And this is a one-directional, two-directional. We even have like multi-directional strain gauges. So what happens is that you're pulling this wire, for example, and it becomes thinner and longer. So now you have a wire that it doesn't become 2L, but let's assume it becomes 2L, and A becomes half of the original A. So if L is 2L and A is half the original A, R, and this, I'm going to call this R1, and this is going to be R2. R2 would be 4 times the R1. Okay. Usually it's not going to be this extreme. Obviously, if you pull it this much, it's going to break. But it's going to be like 5 to 10% if you pull that much, and you're going to see a resistance difference. So imagine if we put this in a bridge inside the concrete, the sensor that I already gave you. Please look at it and pass it to your friends. You can directly put it into the concrete. We can, put a microprocessor in it that has a wireless transmission. Could put a battery in it. Sometimes it could last for a few months, up to a few years. And then each time a truck passes, the bridge starts to bend a little bit. The stress sensor is pushing. And the same thing on the poles as well. So when a truck passes, this strain gauge is compressing, and it's the opposite when you stretch it compared to compress it. And then you can measure how much stress is on this bridge. So using basic principles and by measuring this resistance, you can measure how much stress we have on the system. This is another type of sensor that we use in aerospace. It's called a non-destructive testing, and it's an ultrasound transducer. Why do we use an ultrasound transducer? You may ask, why don't we put a gauge inside? This is the rocket uses, like this one uses a hydrogen and oxygen tank. It's very dangerous, highly flammable, hydrogen and oxygen as well. It's going to be dangerous. So you can't put a sensor directly in it. You don't want to put any holes around the tank. What you can do is you can put ultrasound sensors out of the tank, and it will send ultrasonic waves, and it has a transmitter and receiver, and by analyzing that, you can measure how much fuel you have in each tank. This is a normal ultrasonic sensor that is used for distance. It's good to see one. I don't know. I think most of you have already seen these. It's going to be, it has a T and a R. TX means the transmitter, and RX is the receiver. So the basic principle of this is the same. When you have a tank, a water tank, you knock on it, you can hear it, or truck drivers usually hammer the tire to see if there's air in it. If you have a higher reflex, it means the pressure inside is higher, so you can measure the inside pressure and density of that. We all know how a hollow tank sounds like when you fill it out. It's going to be less resonance and a less noise when it's filled out. Yeah. Do you have any questions about this? Now, a typical ultrasonic transistor looks like this. I've already included one. The sensor that I gave you, that's an ultrasonic sensor. An ultrasonic sensor like that is usually used to find distance. You would find that in a lot of, if your car has a backup sensor, the proximity sensor that beeps, it's most likely an ultrasonic sensor. So an ultrasonic is very good for detecting distances, especially short distances. You have a transmitter and we have a receiver. And the way that it works is the transmitter transmits a sound wave. It hits a target or an obstacle. And what happens is sound wave is coming back. Now, the way that we calculate the distance is that we know that the speed of sound is like 330 meters per second. And if it takes 1 second for the sound to go from the transmitter and get back to the receiver, and we have a timer clock here in the microcontroller. So we send a pulse, we wait, and we listen until we get that pulse. If it takes 1 second for it to go and come back, what's the difference between the wall and the sensor? It's going to be 330 divided by 2. It's going to be 165 meters, for example. Because it took half a second for it to go and another half a second for it to come back. So the distance between the sensor and the wall is 165 meters. An ultrasound sensor is not actually, doesn't work in anything above like 50, 60 meters. It doesn't work because that sound gets, scattered, and it's very sensitive to distance. Usually we work for anything less than 10 meters, and it works very good on anything less than 10 meters. So it's very good if you have you want a parking sensor. These are ideal for a parking sensor or proximity sensors. These are ideal. So anything above like 20, 30 meters, we're going to use radar. Radar is great for measuring long distances. LiDAR is very good for mapping a 3D system. And radar and ultrasonic, they have the same principle. Instead of sending sound wave, they would send radar waves. It's like high frequency, more accurate, faster, and it doesn't decay in longer distances. But ultrasonic is super cheap compared to radar. So radar sensor is $500 to $1,000. These are $2. The one that I gave you is like 20 cents, something like that. Super cheap. In cars, they are like $10, $20. So you can put 10 of them on your bumper. It's going to cost $50 for the manufacturer. Easy to replace, and they are very durable. The ones on the car have the transmitter receiver inside each other. So if you look into your bumper, usually you would see a round shape inside on the bumper. And this is just for the Arduino Uno that you want to use. You can use this one that I already gave you. Now you have different type of sensors as well, and I'm going to give this to you. Before I give it to you, I want to mention something else. So ultrasonic sensor is very good for measuring distances. I had students using ultrasound to, for example, to measure the amount of water in a tank. You can, install it on top of the tank, and the more water you put, it's going to be smaller distance. So you can measure, for example, how much water you have in a tank. So imagine you have a bucket, you put an ultrasound sensor on top, and you can measure the level of water. So different applications for this. There's a problem though with ultrasonic. Ultrasound sensors depend on the speed of sound. And the speed of sound is different at different temperatures. We know if we have like a cold weather, we have more dense air. If we have a hot weather, it's less dense. Also, humidity has an effect. So if you have more humidity, you're going to have a different speed in the sound compared to lower humidity. So if an ultrasonic sensor shows like a density of 1 meter in Houston, if you bring the same thing to Amarillo, it's going to show you something different. It's going to be a little bit of error. So you have to adjust that. Previously, we had a potentiometer pot that we could adjust it. Now they do it automatically, so they measure temperature and they correct the error if you want something very accurate. If you don't want accurate, you just want to, if you want to measure something, if you have like a scale, you want to measure like distance between two walls, you're a carpenter or something, these are not very accurate because depending on the temperature, humidity, there's error on it. So that's the reason they use infrared or LiDAR. But if you want to just have a park sensor that gives you a beep that you know close to something, 1 or 2 centimeters or 10 centimeters doesn't make any difference. And the speed of sound is obviously different in water as well. Water is actually a very good medium for sound. So sound travels very, very well. Those sensors that we use on the water is called the sonar. It's the same principle again. They use it for submarines or detecting fish or a lot of different applications. Another application for sound sensor is ultrasound. Ultrasound uses a high frequency and it's used for medical imaging and so on. So temperature, humidity has an effect on ultrasound sensors because it has an effect on the sound waves, but most parts negligible. But if you want to measure something very accurate, like the distance between me and this wall, you have to put into account the temperature, humidity, air pressure, and so on. Another type, the different types of sensors that you see are utilized in vehicles. This is just a few of them. And you can see we have different sensors such as the accelerometer, the oxygen sensor, the airflow sensor, the water temperature sensor, the oil pressure sensor, and I've already included the oxygen sensor. You can see it on top. And also the oil pressure sensor. I didn't have enough space to add all of that. And the CO, carbon monoxide sensor. Now, in the new cars, you have multiple of these sensors. So you may have a CO sensor in the exhaust. You may have one on the intake or immediately after the motor. And depending on how much CO gas is there, it will manage the throttle. Right now, they don't use the old carburetors. They use injection. But the problem is in a cold day like today, you're going to have a different, the engine is cold and the air is more dense. So you may have a misfire or something like that. And that's the reason you have to adjust your fuel depending on the temperature and the temperature of air and the amount of oxygen coming in. That's the reason we have the oxygen sensor. It measures the oxygen coming inside the motor, for example, and adjusts the fuel according to that. If you put too much fuel, it's not going to burn properly. You're going to have black smoke. If you have too little, you're going to have, you're going to be underpowered, and sometimes you have actually white smoke as well. So you have to have the right amount of mixture of fuel and oxygen. And The airflow sensor, again, measures the amount of air coming in. And if it's too low, usually the oxygen is too low, and you're going to get an error, for example, of that. And the water temperature obviously measures the temperature of the engine. If it goes too high, it's going to damage your engine. Oil pressure is going to be the same. If you're going to have some debris in the engine, it's going to block the oil pressure. You're not going to have enough oil pressure coming in. And this is just some of them. I can mention like 100 other different sensors in the car that is not mentioned here. Can you mention a few sensors that we have in the cars, in nowadays cars? Tire pressure, perfect. Tire pressure is one. Some of them are directly inside the tires right now. The small ones, they are battery powered. They still send wirelessly signals. That's one. Another sensor that you can think of. I'm sorry? Transmission temperature, yes. These a 4x4 off-road, most of them have it. Normal cars don't usually, but yes. Any other? So radar is another one, and the ones that have cruise control. The speed sensor or cruise control sensors as well. Some cars have range sensors that automatically turn on and off your wiper. Some cars have auto dimming lights. So usually they have a sensor or camera on top. And if someone has their high beam on, they will automatically, or sees the car coming in at night, it will automatically put the high beam down. Some of them have line detection or cameras in the front. You may ask, so one other type of sensor is a sensor that they put in the fuel tank that actually measures the amount of octane. So if a car has a turbocharged or a supercharged, they usually perform better on high octane gas. But the thing is, you have to adjust the fuel. So what it does is the car knows, most of these new cars know what type of gas you put. So if you put an octane of 87, it's going to adjust the airflow sensor and the injectors to pump different values so it has peak performance and doesn't have knocking in the engine. So when you put 87, some people may think it's going to damage the motor, but there are sensors that would mitigate that. Or you put like 92 because the fire angle, everything. Fire angle is one, and ignition. There are lots and lots of sensors that I could just mention. Airbag sensors. Airbag sensors are usually on the front of the chassis, and I would show you how they work. Very interesting. And an accelerometer, that's the type of accelerometer. Cabin sensors that you have a lot, like air sensors, air purity sensor, temperature, like air temperature sensors. If you have an automatic air conditioning system, it has a thermostat, probably. We have approximate sensors when you have your key in your pocket and you have a keyless car, detects the key. So it's like thousands of sensors in the car. And there are sometimes 10 or 20 different sensors in the gearbox if you have a automatic transmission, detecting like which gear is optimal, and so on. The RPM sensor. So these are just some of the sensors that we have in a car. Another type of sensor is the biomedical sensors. This is an example of an ultrasound transducer. It uses principles of sound again, and you've seen this a lot. Again, it has a transmitter and a receiver. And part of my PhD actually was biomedical signals. I worked with EKG, or what we call here in the US, ECG, or electrocardiogram, that measures the difference in electrical pulses from the heart. There's an SA node. I don't want to go into the biology, but that gives a signal that you can easily determine if someone is having a heart attack or arrhythmia. Same thing that you have on your Apple Watch. If it has an ECG signal, you have to put your finger on the volume knob. Usually it gives you the EKG signal, what we call, and it could detect if someone is having arrhythmia. EKG signal could be even determine if someone is going to have a heart attack, sometimes 10 days before they even have the physical, symptoms. Another sensor is the PPG, or for the polyasmogram sensor that we call. That is the sensor that are used in detecting blood oxygen levels, and it also measures heart rate. That's the sensor that you see under the smartwatches and wearables. It has a light. That's a light sensor. Usually it's an infrared or a green light that you see on your smartwatches. It has a transmitter, receiver. It sends a light signal, and you can actually detect your heart rate using the PPG. If it uses two different lights, you can measure the oxygen level as well. The ones that you put on the finger, have you seen those, the pulse oximeters? So 20 years ago, before this, they had to get a blood sample. It took 24 to 48 hours to determine how much oxygen is in the blood. Now you just put this on, it's non-invasive pretty fast. And if you want, I can explain more how these different sensors work. But there are dozens of different sensors that work that are used in biomedical and medical applications. Now, an ultrasound sensor, a transducer probe looks like this. They usually put a gel on the skin. The reason that they pull the gel is because if there is a distance, a gap between the skin and the probe, the sound wave is just going to hit the skin and bounce back. So it must have perfect contact. That's the reason they put like a special gel and they press so it's full contact with the body, and then you can see inside the body, the organs used for a lot of different applications, non-invasive. It doesn't cause any harm. One of the safest methods. Before that, if someone had wanted to look into inside someone's kidney to see if they have kidney stone, they have to literally, open the person and see if they have kidney stones. But now we have a ultrasonic or MRI devices which are much more advanced, CT, PET scan, so all of those huge advances in the medical field. I would say now most doctors are acting as more and more as like technicians, especially with the rise of AI, because if a radiologist doesn't have these equipments, there's nothing they can do without an ultrasound or an MRI device. So the basics of the science from 40, 50 years ago, the organs and the anatomy of the body hasn't been changed. There isn't anything new that we didn't know 50 years, 100 years ago. The only thing has advanced significantly is the technology. We have now tools at our disposal like MRI, fMRI that could see inside the body without cutting someone open, and we could have a lot of new treatments as well. And with the rise of AI, I saw yesterday that One Health is partnering with Amazon. They are giving them their AI tool. ChatGPT and Palantir are also partnering with physicians, and they're giving them these AI tools. And Microsoft has one that you just put in a picture and with some symptoms, and it gives a very accurate, like 99.9% accurate diagnostic. So doctors could spend more time on the treatment side. The diagnostic, you just take a blood sample and an image, and the computer just does all the diagnostics. There are a lot of tools, smartphone apps that you just take a picture from a mole and it determines if it's cancerous or not. Its accuracy is 99%. That was originally developed for NASA. Google developed it because these astronauts, they don't want to bring them back to check a mole or something. So they take a picture and you can see if someone has with AI. So it's becoming very, very advanced. It's going to accelerate early detection for cancer and other type of diseases and managing chronic diseases. 30, 40 years ago, if you wanted to take a blood glucose, blood sugar level, you had to take a blood sample, go to a hospital or a clinic, take a blood sample, and it would take 24 hours. After 24 hours, your blood sugar would go up or down. Now you just take an at-home blood test. Or another example for this is going to be the blood pressure. Blood pressure actually uses a strain gauge and a pump. And the blood pressure sensor has like a little microphone thing that gets the data. There is a signal, we call it the knock-knock sound. It's called a knock-knock. And you can hear it, actually. And you can do it at home. It takes a few minutes. What it does, it pumps and it blocks the arteries. And then it slowly releases it. And it starts the sound, the knock-knock sound that we say. And the first sound that we hear, that pressure is the systolic, and the last one is the diastolic. So systolic and diastolic, we can determine the blood pressure, for example. Now the medicine is becoming personalized, meaning 10 years ago, 5 years ago, you had to go to a clinic. Your blood pressure actually is maximum in the morning, goes down in the evening. So when a person went to a doctor, their blood pressure may be normal in the afternoon, but they had hypertension during the night, and they may have a stroke or something. But now with these wearable devices like a smartwatch, you can monitor your heart rate 24/7. It gives you notification, alarms if your heart rate goes up. Arrhythmia doesn't show up. Sometimes it just shows up and that goes away for a week. Now they put Holter monitor devices. I don't know if you've seen those. The person lives with it for a week, and they have 1 week of data of their heart rate. So it's becoming very, very advanced, very good field if you want to continue electrical engineering. The thing that I love about electrical engineering is that, first of all, it's very versatile and vast. You can do power systems, control systems, electronics, communication systems, biomedical, robotics, and AI. It's just accelerating everything. Other types of engineering fields, I would say like civil, or it doesn't have that much space to expand. But if you want to continue with a graduate in different fields, there's a lot of opportunity in medical, biomedical devices fields, and very high-paying jobs as well. So this is a typical instrumentation system and how this looks like. The sensors that I gave you, these are a bunch of different sensors. These are just, I think it's 48 different sensors, from sound systems to smoke detection to IR to, I think there's also light sensors, yes, water level sensors, gas sensor. Yeah, and different type of sensors that you can see in here. This is just a small portion of the sensors that we have. pH sensor is another one that they use for measuring the water pH, and also you can measure soil pH as well. And if you have an aquarium, some fish, you may have the pH sensors and the oxygen sensor in there as well for measuring water oxygen, and a TDS sensor, total dissolved solid sensor, that we measure the amount of salt in the water with it. Now, this is a typical instrumentation system. We have the sensor, amplifier, analog to digital converters, or A to D converters, and we have the computer itself. So a sensor converts the measured value into an electrically useful value. It's basically a transducer. A transducer is a device that converts one form of energy, I could say, to another, so mechanical to electrical, for example, or a voltage to current. Then we have the amplifier, which conditions the signal from the sensor. We have the A to D, or analog to digital converters, which changes the signal into a digital format. Then we have the computer itself, which displays, processes, and records the signal. In some sensors, the sensor and amplifier are combined together. Immediately after the sensor, we put an amplifier to amplify that signal. And sometimes we have all of them. So in these, what we call these shields, Arduino shields, you have the sensor, amplifier, and analog to digital converter all together in some of them. So it just gives you digital signals in the output that you could connect then to your microcontroller, which is an Arduino. Now, I'll give you some examples of some sensors, and then we will go through amplifiers, A to D converters, and also the computer or microcontroller part. So the output of a sensor or a transducer is proportional to the quantity of interest. And we have 3 different outputs of these sensors, electrical sensors. It may be voltage, current, or resistance. Voltage, current, or resistance or frequency. So voltage or current are the temperature pressure ones. Resistance is the second type, which is strain gauge, and the frequency is for accelerometers. So again, voltage or current, resistance, and frequency. Now, do you want me to go back? Okay. Do you have any questions up to here? No? Okay. Now, a transducer is a device, as mentioned, that converts one type of energy to another. The input is usually this, called sometimes a sensor, and the output is called the actuator. And this is an example of a transducer, and we have the input, which could be a microphone, for example. The control system, which is the controller, could be a amplifier, an op amp, for example, and the output is a speaker. Now, this is an example of a input and output transducer. On the right, you see a speaker, and on the left, you see a microphone. So a microphone and speaker are basically use the same principles. Interestingly, actually, if you don't have a microphone, you can use a speaker as a microphone as well. So if you don't have, and even a microphone, if you put a little voltage, if you put too much, it's going to blow it. You can actually hear from a microphone as well. Okay, if the microphone is using a diaphragm, we have a different type of microphone that doesn't work that way. But I remember like the old microphones, you can even like hear small sounds from them. But a speaker is easy. You can actually use a speaker and use it as a microphone as well. And then an interesting thing is there are devices, and scientists were able to actually find devices that uses cameras, and this is interesting, to be able to record something. So the way that they do it is they would shine laser on a wall, and when we speak in this room, the wall starts vibrating, and by recording the vibration, you can actually convert that to sound. And scientists have been doing this to actually on your on the TVs, and if you have an Alexa, technically you can do that as well. But you need to just have something that shines on a wall. It could be a laser, it could be a beam light, and measuring if you have a small shadow or something and measuring the vibration, you can convert that to sound. The same thing is real, what we call an remote PPG or RPPG, and we use cameras to measure someone's heart rate. So you can just have a simple camera as someone's sitting, and you could remotely measure their heart rate. You just have to have a small part of skin. Usually forehead is very good, hands are very good. So if you just show your palm of your hand, and it's a very easy process. I can measure your heart rate, and if someone is having arrhythmia or something like that. And another interesting thing is everyone's heart rate is unique, so you can actually identify someone with just their heart rate. So that's another interesting fact. So what we call it remote PPG, and they use it a lot actually. There were a lot of papers during the COVID to be able to use this technology to find, first of all, if someone has a fever, if they have a higher heart rate, it could determine if they have COVID or not. But again, they must be stationed. If they move a lot, that's called the motion noise artifact, or MNA. It's going to be very difficult to do that. Now, how does a microphone or a speaker work? Let's start with the speaker. It has very interesting, and both of them can have the same principles. So, and a speaker, usually at the back, if you look in all speakers, we have a permanent magnet, the round one. How many of you have opened a speaker? Okay, so you see that it has a permanent magnet. If even the speaker blows, you just take that magnet, you can use it. It's a very powerful magnet. The bigger the speaker, more powerful, you're going to be more powerful permanent magnet. And inside that permanent magnet, you will see some small gaps. And in that, we usually have a coil. And what happens is that coil, we pass electric current from it. And for example, if the current is going from top to down here, it generates an electric field, yes? Do you remember what the electric field was from physics? If your finger is the direction of the current, then yes, it's going to be outwards. The direction of the magnetic field will be outward. So if I have an N over here and let's say an N over here, it's going to repel each other and this is going to move. When this moves, it moves the diaphragm. So the whole thing is going to move. So this whole thing is vibrating. Now imagine that we have an AC signal. It's changing like 30, 40 times per second. So it's N and then it's S. So it's pulling, pushing, and it's moving the whole system. Okay. If you put a very loud music, usually the thing happens, you're gonna rupture the diaphragm. Or most cases when a speaker blows is that wiring, it's a very thin copper wire, it's just gonna burn out because you put like too much current on it and it's gonna just melt. The insulation is gonna melt. Okay, so this is the way that a speaker works. Very simple. And depending on the size of the diaphragm, you're going to have like a bass or a tweeter or something like that. So it depends on the size and what frequency it could, pass. If it's too small, it's the tweeter part. It moves very fast, high frequency, and then you have lower frequency, which is the... So if someone has an electric guitar, I would show them how actually the system works. Now the microphone is the opposite. We again have a flexible diaphragm, and the sound wave hits that. This is a passive element. That one you have to give it power. This one produces its own power. And when this is moving, the coil is moving throughout this permanent magnetic field. When you have a magnetic field passing the coil, it generates current. It's the principle of motors as well. Now you're generating a small signal. It's usually around millivolts. And then you have an amplifier, you amplify it, and you get sound. Another type of microphone is one we call dielectric microphones. So there are a type of, actually there's a type of material that when you squeeze it, it's going to generate a little bit of electricity. Okay, it's dielectrics. And sometimes we build microphones out of that. Those are passive microphones. And when you squeeze it, it generates a little bit of, it's a type of material that when you squeeze or when you expand, it's going to generate a little bit of current. So that's another type of microphone that we can build. Do you have any questions from this?
Why do some microphones require power to get through?
Okay, those are active microphones. Again, they are using that to amplify the signal. So you're going to have an amplified signal. And it's best to amplify the signal at the source. Those are better ones because when you do that, you have a better signal to noise ratio. You're going to learn that in signal systems. You want to have the best signal to noise ratio. If the signal moves through the wires, it's going to reduce the signal and it's going to gather noise, and then you have a noisy signal. So it's best thing that it's amplified at the source. Great question, by the way. Any other question? No. That's the reason if you bring a phone close to a microphone, you have that magnetic field interfering with this and you have that humming sound. If you bring like another magnet, it's going to interfere with this. Is it clear? Can I go to the next? Okay. Now, for a good transducer, it must have certain properties, or it has a certain requirements. And some of them, first is ruggedness, capability of withstanding overload. We don't want it to break after the first time we record something. It's going to last a lot. Second thing is going to be linearity. Input-output characteristics should be linear, meaning if I speak on a low tone and a very high tone, you're going to have the same results in the output. It shouldn't, cut the higher frequency or the lower frequency. It must be linear. Other thing is repeatability, and you should be able to reproduce the signal in day, night, in the winter and summer, rainy days. You have to be in different applications, different environments. You have to be able to repeat that. So if I build a sensor, it works well in Houston or doesn't work in Amarillo, imagine you build a microphone that just works in Houston. So it's worthless. Another thing is high output signal quality. And again, this is a signal to noise ratio. It must be high. We want to have a very good signal quality. Obviously, a microphone, for example, that is low quality, it's not going to work for us. You can hand this around and look at them. And this mainly determines the price. That's the reason we have a $10 microphone and $2,000 microphones, depending on the quality, the wire inside, the magnet, diaphragm, all of that. Again, we have high reliability and stability. We don't want it to last a week. Good dynamic response. And this high reliability and stability and ruggedness is very important. For example, in a car, a CO sensor or a CO2 sensor or an oxygen sensor should last thousands of miles, 100,000 miles, and it works under extreme condition. So the temperature is constantly above 150, 160 Fahrenheit. It's very hot. The motor gets very hot, and it's inside the motor. You can't reach it. So imagine if the oxygen sensor goes out in the middle of the desert, you're going to be strained. Or the gas tank sensor. So these have to work over and over for years and years. And sometimes these sensors are in very sensitive spots. If you want to take out, for example, a oil pressure sensor, you have to disassemble, for example, the whole engine. It takes like 2 days. For a $10 sensor, you have to pay $2,000 in labor. And that actually happens a lot, especially in German cars. I've seen that a lot. You spend like 20, 30 hours to change a valve or a screw that is $2, $1. So we want that that's the reason in some cars, like Japanese car, we have redundancy. We have 2 or 3 sensors. So if one goes out, the other one is still working. Yes?
Oh, nothing. I was just going to say that, and like LS2, they actually have them behind the intake.
Yeah.
So it's really easy, relatively easy to get to, rather than, like in German cars.
Yeah, the German cars, you have to disassemble like the whole front end to get to one sensor. Even the oil filter is in a place that you can't reach. So the philosophy of building cars is different. Toyota the philosophy is that you take this car, you take it to the Sahara, you never change the oil, and it's supposed to work for 4 years. But a German philosophy is that, is there anyone that would not actually change their oil every 2,000 miles? They think that everything must be done, all services must be done in a timely manner. So the cars are designed, they put it, the engines are all under stress, turbocharged, supercharged. They take like 300 horsepower from a 2-liter engine because it's under stress. But Toyota cars, usually the engine is under stress, meaning they get like 150 horsepower from a 2-liter engine without supercharge. So the motor lasts longer. So depend. That's more complicated. You need a lot of sensors and the Toyotas don't. And this is an example. I'm mentioning this. This is an example of different manufacturing building systems and so on. Next thing, we have the good dynamic response. Output should be faithful to input when taken as a function of time. And then we shouldn't have delays. We shouldn't have, especially delays are very, very important as well. And we shouldn't have no hysteresis. Hysteresis means, technically hysteresis is a memory. Meaning if you put a stress on a sensor, the sensor shouldn't deform, let's say. It shouldn't show a bias value. And one example that I could give, if you put a steel, a nail on a magnetic field, And if you keep it there for a few hours, that nail would become magnetic. Okay, so imagine if that is a part of a sensor. Now the sensor has shifted, the measurements have shifted. So we shouldn't have that hysteresis effect, meaning shouldn't deform or keep the previous measurements. And then we have the residual deformation. Should be no deformation, no removal of local after long periods of application. It's the same again with the deformation with the sensors. If we have a strain gauge, let's give you an example. When you stretch that strain gauge, when you leave the stress, it should go back to its original place. If it stays there, you have deformation, the strain gauge doesn't work anymore. Okay. Now, some classifications of transducers. We have primary and secondary transducer. We have active and passive transducers. We have analog and digital transducers, and we have transducers and inverse transducer. So an inverse transducer converts electric quantity to a non-electric quantity. The transducer converts a non-electric to electric. Now, these are some examples of active and passive transducers. Some examples of active transducers. You may have this in your first exam. I had these questions in my first exam last semesters. Active transducer, like a photovoltaic system, these generate their own electricity. We have the thermoelectric, piezoelectric, and electromagnetic. Piezoelectric is the same thing that I mentioned, kind of material that when you press, it generates electricity, a little bit of electricity. It's good for pressure sensor and also very good for microphones as well, some microphones, and electromagnetic sensors as well. So these active transducers, they have an active element which generates power. And then we have passive transducers, such as variable resistance, like photoconductors, strain gauge, and thermistors. They don't generate their own power. They require an external source of power to power them and to be able to measure it. And photoconductors, when you put a photo on it, and there is a conductor here as well, the resistance changes. They are usually used in, for example, dusk to dawn sensors. If you want to turn on a light when it's night and you want to turn it off when it's during the day. Let me see if, I think we have one here. I can't see it, but it has this photoresistors on them. No, that isn't one. Yeah. Yep, it's this one actually. You can see the photoresistor or photoconductor, what we call sometimes, on at the end of this. Yeah, this one is the photoconductor. Now, then we have optoelectronics, passive transducers like photoemissive and photojunction. And we have variable reactance like inductive, such as the variable reluctance, variable permeability, LVDT, eddy current, and capacitive like variable area, variable separation, and variable permittivity. Okay. Now, in active transducers, the output energy of active transducer is supplied entirely or almost entirely by its input signal, meaning they produce their own power or energy. And the passive transducer have an auxiliary source of power. This power source is necessary for the operation of passive transducers. These examples, like the microphone, some microphones are passive. We have also active microphones, the ones that use the piezoelectric. But this is an example of a microphone, which is this type is a passive transducer. And then we have the thermocouple, which is an active transducer. So another category is primary sensing elements. We have, these are called sometimes the pickup sensor or transducer. It detects the physical variable to be measured, for example, pressure, temperature, rate of flow, etc., and converts the signal into a more usable form. In practice, the physical variable is usually transformed into a mechanical or an electrical signal. Now, among the sensors that I will recommend that you look at all of them, this, for example, does anyone know what type of sensor is this? Has any of you seen this? No. This is called a DHT 112 or 111. It's a humidity sensor, and some of them it's combined. It's a humidity temperature sensor, okay? What type of sensor do you think that is? Is it an active or a passive sensor?
This one
Mhm.
should be an active. It should
Yes,
be
it's an-
sound.
No, the humidity part is a passive sensor. Temperature could be active or passive, but this one is, again, it's a passive sensor. And for the passive sensors, you can see they have all a power source as well. Like this one is an infrared sensor. This one is actually for detecting fire, and it's a heat-seeking, and you can really use it on a robot to follow the heat. We have light sensors. We have pressure sensors here, and I would recommend this is actually a servo motor in it. Servo motor has a sensor as well in it, a feedback sensor that sends some information back to the microcontroller, like the angle and so on. Some of them have torque sensors as well. Does anyone know what's the difference between a microcontroller and a microprocessor? Is the Arduino a microcontroller or a microprocessor? Arduino is a microcontroller. What about a Raspberry Pi? A Raspberry Pi 4, not the Nanomic. That's a processor. So a processor can process the data. For example, if you have an image, you want to do image processing, Raspberry Pi is the way to go. It's like a computer, a small version of a computer. A microcontroller is a less powerful device that is good for controlling stuff. It's good for industrial use. It doesn't have an operation system like a microprocessor, and it's cheaper, usually much cheaper. And microcontrollers are low power, very fast. If you want to measure a value like a sensor or control something valve, they're ideal for that. Microprocessors are good for processing signals and images and doing heavy loading stuff. You can use a microprocessor to do microcontroller's job as well, but the microcontroller cannot usually do the microprocessor's job. So a microprocessor is going to be more powerful. Microcontroller, some of them also do a little bit of processing, but they are mainly not built for that. They are mainly built for, maximum, filtering a signal, A to D conversion, and so on. Now, the reason that I said this is the microcontrollers and microprocessors, they have digital and analog inputs, but mainly we are interested in using the digital. That's the reason a microcontroller like the Arduino, they usually have just one analog or two analog inputs maximum and 20 digital inputs. The same thing is true for microprocessors. Some of them even don't have an analog input. So before you even feed that to a microprocessor, it must be converted to digital before. Now, you are all familiar with analog and digital signals. Analog signal is you see an analog example on the left. It's continuous, and then you have a digital. Digital means a digit base or discrete signal. Now, the reason that the majority of the processing that we do on digital is because it's much easier to process digital signals. You can easily, manipulate the signal, get rid of the noise. Noise extraction is very easy. compression of the data is easy in digital. Transmission is very easy as well because you can easily compress that. But recently, in the past 5 years, analog processors have become very popular as well. There's been a shift. Like 20 years ago, they were almost extinct, but now they're doing a comeback. In certain scenarios, they are actually good. So for example, in AI, they realized there was a lot of application for analog processors. That's the reason a lot of companies are interested in, and they're actually heavily investing in analog processors. But for the course, 99% of the time you're working with digital. So when you work with digital, everything that you see around you and the environment around us is analog. Okay, pictures, smell, sound, temperature, everything is analog. Okay, in real world, everything is. We don't have such a thing as a digital. If pictures were digital, you would see everything pixelated, or a sound discrete. So everything in nature is analog. When we measure it, we have to convert it to digital. Okay, so for example, on the left, you can see this is a thermocouple that measures temperature, and it's measuring it in a continuous way. And first thing that we need to do is to condition the signal. Conditioning the signal meaning getting rid of the noise, amplifying it maybe, and then converting it to digital. And I'll explain how we do that. On the left, you have an analog system. On the right, it has a digital. This digital system on the right, it has a disk with a slot in it, and it has a transmitter and a detector, which is a laser or infrared. It sends the laser, and the moment the laser passes that slot, the light passes, and you get 1 round per minute, for example. So you can see, you can count these 1, 2, and you can count it, and you can have like 100 rounds per minute or second or something like that. So you can see on the right, it's discrete or digital. On the left, it's analog. Now, we are interested in digital. Therefore, we want to convert analog to digital. How do we convert analog signal to digital? So if I have a signal like this, and I want to convert it, and this is an analog signal, I want to convert it to digital. How can I do it? Yes. And how do I do it? Do you know? Does anyone know how we do that? Yes. Yes. So imagine I give you the signal, and I ask, make it a digital. How can you do that? Imagine you have the signal is coming from a function generator. It's an analog signal, and I ask you to convert this to digital. So we do this through a process called sampling, meaning with a fixed intervals, let's say every 0.1 second, I take a sample from that signal, and I record that, and I save it somewhere. So if I do the sampling now, the output signal would look like this. The output signal is going to look like this. And you can see that this is this, this is this, and so on. So this was the analog, this is the digital one. So through a process called sampling, we can convert an analog signal to a digital signal. Now, if I want to convert this back to analogs, for example, if I want to play it on a speaker, and the original was an analog signal, only thing that I need to do, how can I do it? I could simply connect these signals to each other, okay? So connecting them using what we call an envelope detector. Now, how can I take the sampling with a simple switch? Imagine I have a switch connected to the upper one, and I can control when to open and close the switch. That's going to be my sampling rate. Okay. Now you see that the analog on the top and the analog that we reproduced after analyzing the digital is a little different. That is because of a sampling rate. So if our sampling rate is too far apart, imagine if I had a sampling rate that looks like this. I have one sample here, one over here, and one over here. Then my signal will look like this. Okay. So the higher the sampling rate is, so if I have a sampling rate that looks like this on the upper one, if you look, you're going to have a better representation of it. So if my sampling rate is even higher, like this, it's going to be closer to the original signal. So higher sampling rates, you're going to have a better representation of that. But that causes a problem. Sometimes we don't even need to have that much of sampling rate because there's not enough useful information in between those samples. Let me give you an example. If you want to download an MP3, sometimes it gives you two options, like, do you want this to be at 126 kilohertz per second or 320? The higher one means the higher sampling rate. But the thing is, human ear is sensitive to a certain point. We cannot hear anything above 20 kilohertz. It's between 20 hertz and 20 kilohertz. So if I have a sound that is 40, 50 kilohertz and the sampling rate is 2 megahertz, it's not going to work. You're not going to hear the details. The same for the eye. Your human eye is capable of separating 16 million colors. So if you have a display that shows 300 million colors, 274 million of that we can't even differentiate between different shades of pink, for example. So sometimes we cannot, above a certain quality, it's not making a lot of difference. Like in the previous one, if you want to take temperature, temperature goes a little bit down in 0.1 second. It's not going to make a difference in our thermostat. So we want to actually put the sampling further apart, because if we do that, we spend less energy on the analog to digital converter, and it's less data to transmit. Higher sampling rate means if I double the sample rate, I'm going to double the data. And if you're going to send this in long distance, like an image that you want to compress and send it on the internet, you don't want to have a high sampling rate. So up to a certain point, it gives you information. After that, it's redundant. And below that, it actually eliminates a lot of data, useful data, and it becomes useless. So you have to find the sweet spot on the sampling rate. What your sampling rate? For what application? If you are measuring temperature, you don't need to do it every second. You can do it every 2 minutes. So you take a sample here, another one here. Okay? But if this was sound, you wanted to take samples every 0.1 second. Okay? It's like you're recording Taylor Swift, and if you don't have a good sampling rate, you can hear something like, I don't know, Mick Jagger or something like that. So it's going to be something that it's completely out of frequency, a different, something that you won't even recognize. Giving you an example, it's not technically like that, but this is a metaphor. So sampling rates depends on how much information and what's the sensitivity. Now, this is an example of this is resistive transducers. I think that's enough for today. Up to here, we don't have enough time to finish this. But yes, just know that analog to digital, and for digital to analog, again, if we connect these together, if this digital signal was like this, we just connect them together and create analog. And analog could have binaries like 0 and 1, as you mentioned, or we can have multi-level. So we can have one that is 1, 1, 1, for example, that is here, 1, 1, 0 is here, 1, 0, 1 is here, for example, and 0, 0, 0 is down here. So you can have multi-levels. So we can have something that looks like a stair, or we can have zeros and ones. So the ones that have like a multi-bit system, they give more information. And you can compress more data in a certain time. So it's better for transmission as well. Okay, that's it. Yes. Yes, the time interval. Yes. And the number of bits, if you want to do a 2-bit, 4-bit, 8-bit, something like that. So you want to have one level, zeros and ones, or in output, you're going to have 2 bits, like 0, 0, 1, 1, something like that. So here, that's a good question, by the way. We have multi-levels. If I had zeros and ones, it would be like 1 or 0, or 1 or 0. But now I have this level, like 5, 6 different levels that I have. So if something is between these two levels, it takes the upper value, for example. There's a whole course for digital and analog communication systems. It's called digital communication. And you're going to learn a lot about that in communication, not communication system 1, 2. Communication system 2. Okay, thank you so much. And I would see you next week.